The microstrip is the absolute workhorse of modern RF and microwave engineering. It is cheap, easy to manufacture on standard printed circuit boards, PCBs, and allows you to mount surface components directly on top. However, unlike a coaxial cable, where the wave is perfectly trapped inside a uniform cylinder of Teflon, the microstrip has a leaky geometry. This fundamental physical trait leads directly to the concepts of the effective dielectric constant and signal dispersion. Here is an in-depth look at how the fields behave, why they change with frequency, and how that distorts your signals.
The inhomogeneous medium. A microstrip line consists of a copper trace on top, a dielectric substrate like FR4 or Rogers material in the middle, and a solid copper ground plane on the bottom. When an electromagnetic wave travels down this trace, the electric and magnetic fields do not stay neatly confined inside the substrate. While the majority of the field lines travel straight down from the trace to the ground plane, a significant portion of them fringe out the sides and arc upward through the air above the board before terminating on the ground plane. Because the wave is traveling through two completely different materials simultaneously, air, εr is approximately 1, and the substrate, εr is 4, this is called an inhomogeneous medium.
2. The effective dielectric constant, epsilon effective. Because the wave has 1 foot in the air and 1 foot in the board, it travels at a speed that is a compromise between the speed of light in air and the slower speed of light in the substrate. We represent this compromise with the effective dielectric constant, epsilon effective. It represents the permittivity of a hypothetical, uniform material that would cause the wave to travel at the exact same speed as it does in your mixed air-substrate microstrip. The value of epsilon effective will always satisfy this rule. 1 is less than epsilon effective and is less than epsilon r of the substrate dielectric constant.
How geometry dictates epsilon f. The exact value of epsilon f depends heavily on the physical dimensions of your trace, specifically the ratio of the trace width, w, to the substrate height, h. Wide trace. If the trace is very wide compared to the board thickness, it acts almost like a parallel plate capacitor. The vast majority of the electric field is trapped directly underneath the trace in the substrate. Only a tiny fraction fringes into the air. Therefore, epsilon f approaches the raw epsilon r of the board. Narrow trace. If the trace is very thin, almost half of the electric field lines will fringe outward and upward into the air. In this extreme, the wave is split almost 50-50 between air and substrate, and epsilon f is approximately the average of the two dielectric constants. At lower microwave frequencies, a highly accurate static approximation of the effective dielectric constant is given by the Hammerstedt and Jensen formula shown here. 3. Signal dispersion, when speed depends on frequency. If epsilon f was a fixed number, life would be easy. But in reality, microstrip is a dispersive transmission line. This means that waves of different frequencies travel at different speeds. To understand why, we have to look at how fields behave as the frequency scales up into the high gigahertz range. The physical mechanism of dispersion. Electromagnetic waves are lazy. They prefer to concentrate their energy in regions of higher permittivity, slower phase velocity. At lower frequencies, e.g. 1 GHz, the field lines are relaxed and spread out widely, fringing significantly into the air. As the frequency increases, e.g. 30 GHz, the fields tighten up. The high-frequency waves pull their energy out of the air and concentrate it more densely into the dielectric substrate directly beneath the trace. Because a higher percentage of the wave's energy is now traveling in the higher epsilon r substrate, the effective dielectric constant, epsilon f, increases as frequency increases. Since phase velocity, Vp, is inversely proportional to the square root of epsilon f, the higher the frequency, the slower the wave travels. 4. The impact, pulse spreading. If you are transmitting a pure, single-frequency sine wave, dispersion doesn't matter much. The wave just travels at one specific speed. But if you are transmitting a sharp, fast digital pulse or a wideband modulated radar signal, dispersion becomes a critical engineering challenge. As we covered with group velocity, a sharp digital pulse is mathematically composed of a fundamental low frequency and dozens of higher frequency harmonics. You inject a clean, square digital pulse into a long microstrip line.
The low-frequency components of that pulse experience a lower epsilon f and travel faster. The high-frequency components experience a higher epsilon f and travel slower. By the time the signal reaches the other end of the board, the high frequencies have fallen behind. The result is that your sharp, crisp digital pulse smears out, widens, and loses its peak amplitude. If the dispersion is severe enough, one pulse will smear right into the next one, causing intersymbol interference, or ISI, and corrupting your data stream. Enjoying this? Smash that like button and subscribe for more RF and microwave engineering content. Drop a comment below with what you want to see next. I'm reading every single one. Let's get back to it. Thank you.